Okay, guys, before we get started, any questions about any material? Anything at all? Any questions? Questions about lab? If you come to lab, you need to make sure you have looked at your data in case something is not quite right. You don't want to find that out after this week, because after this week you will not have a chance to do anything else in the lab. Okay? You sit down and you're like, oh, my bowling point matches nothing. Maybe I should redo it. Well, your chance to redo it is 45 minutes this week. So look at your data before you come to lab. That would be most ideal. Okay, chair confirmations. There are no questions. Question? Which one was that?
The second one at the top.
That's a new one confirmation. New one confirmation?
Yeah, just to make sure I made it right.
On the front car, I see a carbon in the front. It has an ethyl and a chlorine. Yeah? Carbon in the back. Carbon in the back has what on it? Two methyls and a hydrogen. Yeah? I can clean this up a little bit. I've got a carbon with two ethyls. Here's that carbon with two ethyls. It's got a chlorine. And it has a carbon with two methyls and H. Well, we won't draw it in. I'll make this bond angle a little bit better. There we go. That's the compound. Longest continuous chain, 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I got 5 this way, and I got 5, 1, 2, 3, 4, 5 that way. 5 this way, I would only have 2 substituents. 5 this way, I would have 3 substituents. So I'm going to go this way. If this is 1, 2, the first substituent is at 3. If this is 1, first substituent is at 2. That's going to be better. 1, 2, 3, 4, 5. That's a pentane. What's on the pentane? At the 2 position, I have a methyl. At the 3 position, I have a chloro and an ethyl. Alphabetical order, C comes before E. 3 chloro, 3 ethyl, 2 methyl, all one word, pentane. Everybody see how we do? How's it look? You get it right? 3 chloro, 2 ethyl, CM. Yeah? What it looks like to me. Again, we don't have to worry about stereochemistry. This compound doesn't have any stereochemistry, by the way. So there's nothing to worry about anyway. Okay, chair confirmations. We were drawing those last time. Let's pick up. Let's see what's next. We also have our outline here. There's not much on chairs in here, although we'll look at some carbohydrates. Let's move ahead, and we'll see if we need to redraw or whatnot. But let's move ahead for what's on the handout. Identify each as cis or trans. Okay, we talked about drawing a perspective with the dashed and bold. If you have 2 groups and they're both bolded towards you, that's cis, right? Okay. Well, what about if they're drawn like this in chair confirmations? How do you tell? This compound here, are these 2 halogens cis or trans?
Trans.
Well, how you do this is you look at the H that's also there. That H is straight up, right? Sometimes when we draw chairs, you don't have to draw the H's in, but you need to be able to. And if you draw this H in, it's straight down, right? Because that's an up carbon, that's a down. All right. This chlorine is below the H. The bromine is above the H. So they are trans. Over here, the H is down, the H is down. These two halogens are what? Cis. The H is up. The H here is equatorial. Those two halogens are trans. The F is above the H, the chlorine is below the H. Should be pretty straightforward. Show us a perspective drawing. Perspective is where you use dashed and wedged. When you do chair conformations, you do not use dashed or wedged. That's implied in here. You do not use it. We got a cyclohexane. We can draw it flat on the board, although we know in real life it's not flat. It's a chair conformation. Okay? We got, what's the name of this group, by the way? Common name. Isopropyl group. We got isopropyl, a bromo, and a fluoro. Let's put them on the compound. All right? Now, I'm not going to worry about stereochemistry in terms of mirror images. We may end up with a mirror image. I'm not going to worry about it now. Because if we were going to worry about it, we'd have to introduce all stereochemistry to be able to worry about it. We're not doing that until test 2. We got an isopropyl group on one of the carbons. It doesn't matter where you put it. Where you want to put it. There? It doesn't matter. Let's put it right there. Because the compound can rotate. Now that we put that there, though, well, hold on. This is also a tetrahedral. 2 in the plane, 1 forward, 1 back. These things need to be forward and back. Well, let's make it forward. From there, the next groups we have to have correct relative to that one. That is the fluorine. Where does it go? Does it go on the next carbon or does it go on this carbon? What's on the next carbon? Right? So we're going to put it on the next carbon. Which way do we go? Over here next carbon or over there? That's the mirror image thing that I'm not going to ask you to worry about. All right? I'm just going to put it over here. But do I need to draw it dashed or bolded? Well, what's the relationship between these two? Cis or trans? They are cis. So how do I draw the F? Dash. No, they're cis. I need to draw it bolded. Cis. Now, where do you want to put the bromine? On this carbon? No. This is a 1, 2, 4 relationship. 1, 2, 4. The bromine goes here, but is it going to be dashed or bolded?
Dash.
All right, I haven't looked at it yet, but we hear dash. Anybody say anything else? Let's make it dash. So you're saying it's trans to both of those. Trans to the fluorine? Is it trans to the fluorine? Well, the H is down, the H is up. Yeah, down compared to the H, yeah. The bromine is trans to the fluorine, and I bet you a steak dinner it must be trans to that because those are the same. There you go. There it is in a perspective drawing. And we have the relative orientation correct. We have the 1, 2, 4 correct because it's 1, 2, 4 substitute. We're drawing the same compound. But we also have the relative stereochemistry correct. What may not be right is first off, could I have drawn this like this? Could we have done that and been right? Groups are cis. Are they cis here? Mm-hmm. Yeah. Are these two trans? Just like that? Yeah, we could have done that too. These are mirror images. And that's what I'm telling you. Either is fine for now. I'm not quite sure. This only matches one of these. We don't have to worry about it right now. Okay? Either is acceptable right now. Down the road, we need to be able to tell which one of these is that. Okay? They're mirror images. By the way, if I had put the F over here, bolded, that would have been this compound here. Just turned around. Okay? More of that there in test 2. All right, so that's understanding cis and trans. Perspective versus chair conformation. We could have mentioned this down here earlier. When you have a chair conformation, it can so-called ring flip. It can go from one chair to the other. Here, if you're sitting here and the back is here, but it can ring flip. This end can come up and that can go down. And now it's like the chair is sitting this way and your back is here. All right, TV's over here now. Or you can boop, boop, and now the TV's over here. But that can go back and forth. That's sort of like rotating. All right, we say that this can go from here to here, but that's a bond rotation. This is not a bond rotation. Well, it kind of is. The whole thing is sort of pseudo-rotating. But it's certainly not doing this, because you can't do that with a ring. You see, it's going to break it. It's called a ring flip back and forth, from one chair to the other. The question we could ask is, of the two possible chair conformations for a given compound, for example, let's put an isopropyl group on here. Let's put it at the point up, down. Right now, the isopropyl is axial or equatorial? Axial, straight up. If we do a ring flip, what do you think the isopropyl will become? Equatorial, right? Because when you do a ring flip, everything goes. Now see, I broke my models when I tried to twist them. Can't twist it. We do a ring flip, flimsy models. I wish these things were twice the size. Now how's the isopropyl? It should be equatorial. I should know. Okay. See now it's equatorial? And the H is straight down. It's axial. Okay? So which is better? Which chair is best? This one? Or let's go back to the ring flip. Or the ring flip. Well, would the isopropyl rather be axial or equatorial? Equatorial. Equatorial has more room. Again, another reason being, oh, I really screwed it up. All my bonds are quite weak now. Reason being is these two H's are sticking up, and as this thing can rotate. But as it rotates, see how it's knocking it against that one? What's that called?
Flagship.
1,3 diaxial interactions. Because if that's 1, then this would be 3. All right? It prefers to be the other. That is right here. Okay? If you got a methyl on the ring, it can ring flip back and forth. I don't have my H's drawn in here. You can do it for practice. For example, that H is right here, right? And this H is straight down, yeah? Okay? We can say which is favored. Well, this is favored because your group is equatorial. Your substituent, your non-hydrogen. And this is actually known that at equilibrium, this is 18 times more favored. Right? So as it's hanging out, you know, on a Friday night, it's more likely to be in this conformation. Make sense? Because it's equatorial. Now if you go to T-butyl, if a butyl group is here, the two conformations, the two chair conformations, this one's favored 4,800 to 1. That's because the T-butyl is so much bigger. And so, since it's bigger, it really hates being axial. Because again, that H is right here, and these interact. You wouldn't think so, but that's the main argument. Okay? So the bigger your group, the more and more it's going to prefer equatorial. Huge groups really prefer equatorial. And down below, that's going to be a driving force, is putting that big group equatorial. Just like back over here, we put two big groups anti. Here we're going to want to make sure big group is equatorial. And maybe we may have multiple groups, and so we want to see if we can get multiple groups equatorial. For example, down here, this is the two ring flip chair conformations. Which one's going to be favored? This one. Because the biggest group gets to be where it wants. It rules. Equatorial. By the way, the T-butyl and the methyl, are they cis or trans here? Yes, they're cis. And if you think about it, when they're cis, both groups cannot be equatorial. Because if you drew this equatorial and this equatorial at this positioning, that would be trans. That'd be a different compound. What's the relationship between the cis and trans forms? So this side's favored, right? Okay. Show which of the following the lowest energy conformation? Conformation in being chair conformation with cyclohexanes. Chair is always better than boat. Talked about that. I don't talk about boat anymore. Boat would be where instead of one end up and one end down, is where both ends are up. That's called a boat conformation. But boat is really never good unless you got something else going on because of these sort of flagpole interactions, I think it's called. So we're always looking at chair here. Chair is always the best, but you got two different possible chairs. Okay? Okay. Got two bromines and a fluorine. They're all next to each other. 1, 2, 3. I reckon I'll put a bromine here. Well, no, let's do it this way. That's how I would do it. What's the biggest halogen? Bromine. So I'm going to put it here, but I'm going to put it in the best position, equatorial. And let's draw in the H's that are on these carbons with the substituents, straight up, right? Try and draw the best, so I'm going to put the biggest group equatorial, yeah? All right. Now from there, we got to make sure everything is relative to that. Where does the next bromine go? Here? No, it goes, if that's one, the next one's here. Or there. Again, either would work. You'll get mirror images. That's fine. I'm just going to put it here. But is it going to be axial or equatorial?
Axial.
Well, they're cis. So is it going to be axial or equatorial?
Axial.
Be axial. Common error. You guys say, well, this is cis, so they should both be equatorial. No. No. These are cis, and those are cis, like they should be. But that one's axial, that one's equatorial, and this one's axial. Let's draw in the H. Okay, where do you want to put the fluorine? Here? No, it's 1, 2, 3. 1, 2, the fluorine must go here. We could put it there, and it could be 1, 2, 3 that way. You'd get mirror image. Let's continue this way. Is the fluorine going to be axial or equatorial? Well, the fluorine is trans to both bromines, trans to that bromine, trans to that bromine, so how is it? It should be axial, straight up. And then this H is sort of like this, parallel with that. There's your F right there, that's an F. These two are trans, like they should be. Those two are cis, like they should be. Is this the best conformation? Let's do a ring flip and compare the two conformations. First off, is this the best or can we do better?
You can do better.
Who's saying?
Do better.
How can we do better?
Because there's two halogens in the axial, so if we flip to V2 in the
Okay, let's do a ring flip. I'll do a ring flip exactly like this. I'm going to pull this end down and pull this end up. And we'll do that exactly. In the future, I'll just redraw it from scratch as a ring flip. Pull that down, so now we're doing like this. Okay. This point is actually now down, this point is actually now up. The first bromine is here, but now it is straight down. The second bromine is here, and it is, this should have been a little bit more pointed. My equatorial is coming, that's an up. It's a little, didn't draw it quite as pointed as it should have been. And then the F is here, and then the F is like this. H is straight down. This H is this. We know that when you do a ring flip, this one went from equatorial to axial. This one went from axial to equatorial. And that one went from axial to equatorial. These are your two ring flips. Okay? At equilibrium, which is going to be favored? That's the question. One on the right. Why?
Two groups are equatorial.
Basically, the bromines is a wash. One bromine axial, one bromine equatorial. One bromine axial, one bromine equatorial. It's a wash. So let's look to the fluorine. Here it's equatorial, there it's axial. Which is better? This one's better. Ultimately, you have one of your big bromines is equatorial, same as over there. What makes this better is here the fluorine is also equatorial. Let's look at this compound differently. Here it is on the board. Pretend it's flat. This bromine is coming forward. We may end up with a mirror image. Okay, pretend it's flat. That bromine's forward. The other bromine next door is also forward. Okay, again, pretend it's flat. Can you guys see? Both greens are forward, right? They're both coming towards you. And then the fluorine, the fluorine is over here, but it's going back. So I'm going to make it blue and I'm going to make it go back. I'm praying that we got the right mirror image. There it is on the board. It's drawn flat, but we know it's not really flat. We know that it's really like this. I'm going to turn it here. This up. We got the right mirror image. 50-50 chance, we got it right. Here it is over here now. Bromine is equatorial. This bromine straight down. And this fluorine straight up. You see how it is? We went from that. I just turned it, now it looks like that. Okay? See how, by the way, the fluorine and the bromine are trans. Right? You see how they're trans? I mean, look, that was forward, this one's back. We turn it like this. This one's up compared to the H. That was down compared to the H. Then we did a ring flip. I pulled this end down and moved that end up. And the ring flip looks like this. Now the bromine is straight down. This bromine is equatorial. And then this fluorine should be, model is a little, it should be equatorial, shouldn't it? Yeah, it looks like it goes down is there. Yeah, equatorial. You see? See how we're doing this on the board? We're going from perspective through that, ring flip, and it changes things. Okay, let's see where we're at. Questions? We'll do the next one? Do the next one on your own real quick, if you haven't done it already. We didn't answer the next question. How many groups are equatorial in the best conformation? How many groups are equatorial here in the best? 2. That is, not all 3. All 3 cannot be equatorial here with this configuration, with this stereochemistry. What's going to be the answer here? All right. This group's kind of big. These 2 may be a wash, or they may sort of both be equatorial. For a couple of reasons, I'm just going to start with this group. It's kind of the bigger one. It doesn't really matter. I usually start here. You can start here if you want. But if you start here, then you got to say, well, the next one is relative to that. Okay? Since it's pretty big, I'm going to draw it equatorial. Isopropyl equatorial. Next, chlorine. We put a chlorine here? No. The next chlorine is 3 away. If that's 1, 2, 3. 1, 2, 3. Do I draw it axial or equatorial? Equatorial. The H is axial. Because these are cis, right? How do we know they're cis? Well, they're both dashed. They're both going back. All right? These are cis. They're both below the H. Next chlorine goes here. How does it go? Axial. H is here. All these are cis, right? It's all cis. Down, down, down. All of them down compared to the H's. Is this the best conformation, or do we need to draw a ring flip? I have an isopropyl equatorial, 1 chlorine equatorial, and 1 axial. So I have equatorial, equatorial, and axial. With the equatorial being the isopropyl, okay, I-pro. Isopropyl. If I do a ring flip, what do you imagine it's going to look like? The isopropyl would then be what? Axial. One chlorine will be axial, and the other chlorine will be equatorial. So is it going to be better? Do we even need to draw a ring flip? I don't think so. This is the best one right here. Could be the mirror image, just for the record. I don't want to be accused of drawing mirror images later on. We're good? That's it. What's the answer to the question? How many groups are equatorial? 2. Not all 3 in this case. Could we have a compound where all 3 were? Yes. If this chlorine was here, then all 3 would be equatorial. If that chlorine was there, how would we need to change our perspective drawing? The furthest chlorine would need to be trans. So if this was instead bolded, that compound, you could have all 3 equatorial. That'd be really good. But we don't have that compound. Question. Somebody have a question?
How do you know that's axial?
How do we know which is axial?
The bottom chlorine?
This one? Because that's equatorial. Straight down is axial. Straight up is axial. The things that are to the side or parallel to these bonds, that's your equatorial, right? Your axials, if you set it down on the table, okay, your 3 axials will hit the table. It's lopsided because I got a bond there, but 3 things down, and then turn it over, you got 3 things, there you go. The 3 things straight down are what's hitting the table. The other things are coming to the side. Okay, let's see where we're at. Any questions on this? Let me show you. You'll see chair conformations in biochemistry. On the very back of the notes handout, when you look at carbohydrates, carbohydrates can exist in an open chain form or a ring form. The ring form is a 6-membered ring. And the 6-membered ring it does contain an oxygen in the ring, so it's not a cyclohexane. It's got an oxygen, it's not just 6 carbons. But it's a 6-membered ring, and it's typically shown in chair conformations. All right? And you'll learn about different carbohydrates, the alpha anomer, the beta anomer. This has to do with the positioning of the anomeric OH. This OH here, I believe, and I had biochemistry a long time. The alpha anomer is where this OH is axial. The beta anomer is where that OH is equatorial. Okay? But see, when you move on, you're not going to be retaught chair conformations. You're going to be expected to know that terminology, etc. Okay? So you will see stuff in other places as well. So that's carbohydrates. You can do a little looking at that. Like glucose, etc. Sweet stuff, yeah? Okay, let's see where we're at. We're heading down the home stretch. What have we not covered? Questions?
Can we go over the looking down the 4 to 3 bond on the
Which one?
confirmation report sheet?
Which sheet? Pink or
Purple.
purple? Where? On the front side, the 3rd one?
Yeah.
We're now 4-3, so we want 4 in the front. Nomenclature, we're going to figure that out because I wasn't told here. What's the one end? Is it this or this? This must be the one end because that makes 2,2-dimethyl. Coming this way, you have two substituents at the 2 position. Coming this way, you only have one substituent at the 2 position. 1, 2, 3, 4, 5. 4,3 would be 4,3. So we're standing here and looking down here. Okay? Here. 4 is here, 3 is behind. What do we see on carbon 4? That's the front carbon. Right? I see a methyl coming straight up in the plane. That's a methyl. I indicated it with an ME here. What's on carbon 4 coming towards you guys? Iodine. Correct? I'm holding this molecule here in my hand. The iodine is coming towards you guys. If I'm over here, the iodine's on my left. I see an iodine coming to my left. I'm drawing it on the board. What I see. It's also coming a little bit down. Okay? All these angles here off of one carbon are 109.5 because it's tetrahedral carbons. And so they're always going to be boom, boom, and boom. What's on carbon 4 going behind the board? If I'm over here, it's going that way, it's on my right. What's that? Undrawn hydrogen. Okay? See, here's the board. If you're looking that way, you see an iodine coming towards you. If you guys were sitting over there, the iodine would be coming towards you, off the board. Right? That's what that means. The iodine is coming towards you, off the board. The methyl is straight up on the, is drawn on the board. It's not forward or back. Okay, back carbon, 3. What's straight down to my feet? Not forward or back. You can tell things are forward or back. Things that are drawn just a straight line, that means it's in the plane. And so it's going straight that way, towards my feet. T-butyl. Boom, boom, boom. Tert-butyl. What's on carbon 3 coming towards you guys? Methyl group. So I see it to my left. If I'm over here, it's to my left. Methyl. What's on carbon 3 going to my right? Undrawn hydrogen. There it is. As drawn on the board, it's in a staggered conformation. By the way, that's why we usually do zigzag. Because this is really staggered. All right? At least simplistically it is. You can turn that into non-staggered pretty readily. Okay, is this the best conformation? What's the biggest group on the front? Iodine, huge. Huge iodine. I will try to make it clear. Okay, if this was a chlorine, that would maybe be more clear because chlorine is certainly smaller than iodine. Methyl, pretty small. I would try to not give you something where it's hard to distinguish. Okay? For example, back carbon, which is bigger? H, methyl, or tert-butyl?
Tert-butyl.
Yeah, tert-butyl. Okay? Currently, the two biggest groups are what position? Gauche. Is that good? Could it be ever? Could be. We showed an example, right?
Could be.
But I don't see anything here for it to be. Let's rotate the front, or you can rotate the back, either way. I'm going to rotate the iodine up. So now the iodine is up. That's going to make the methyl come here. We're just turning this like a steering wheel. The H comes here. We didn't do anything to the back. So we've got methyl there, H there, and T-butyl here. And now your two biggest groups are anti, and there's your answer. In the best conformation, what's the dihedral angle between the two methyls? 180? Yes. That's it. Any questions about it? Yeah.
How would you know to start the one on that side instead of the other side?
That's just nomenclature. If you name this, this would be the one position, right?
Well, because it depends if it's like a T-butyl or a dimethyl, because then it would be.
No. You've got substituents at lowest numbers. Where do you want the one position to be instead?
The other side.
Hmm?
The other side.
Here? Well, if it was over there, you would have, the first substituent would be at 2. It would be one substituent at 2. If it was over there, it would be a 2-iodo, 3-methyl, but it would actually be 3-4-4. It would be 3-4-4 trimethyl. That'd be your substituents. If we start over here, you would have 2 methyls at the 2, so it would be a 2-2 and a 3. So it would be a 2-2-3 trimethyl 4-iodo. Which is better? 2-2-3-4 or 2-3-4-4? This is better. Because in both cases we have subs at the 2 position. But coming this way, we have 2 subs at the 2 position. It's a little bit, I mean, it's not a standard example, but hopefully when you see it, it makes sense. Because this is a wash, so you'll start looking at the next numbers, and 2 beats 3. Anything else on this page? Any questions on the daily DQ page? I'm doing some of those. Anybody done any of these? Any questions about any of these? We need to look at one last thing back in the physical properties handout. Questions about the DQ page? Okay, physical properties handout. Let's look at the acid-base extraction. Acid-base extraction is very common. First off, it's a special type of extraction. Extractions are very common using an organic solvent and usually water, 2 phases. And we can then partition a mixture between 2 phases. We can say, okay, some of these compounds are going to go into the water, some of these compounds are going to go into the organic. Then you can separate the 2 layers in a separatory funnel. You have separated components. Acid-base chemistry can also be used in this scenario. Of acid-base chemistry, you can go from a charged species back to a neutral species. Typically, when something's charged, it's going to be more soluble in the water layer. When it's neutral, neutral organic is going to be more soluble in the organic layer. Yeah? And with acid-base chemistry, you can go back and forth between charged and neutral real easy. And for example, we can separate these 2 compounds here. Organic solvent, common one, dichloromethane, it's called, or sometimes called methylene chloride. Organic solvent. Both of these will dissolve in that. They're both neutral compounds. By the way, when you say neutral, I usually mean there's no charge. some of your lab reports, some of you guys are calling things neutral, meaning they're not acidic or basic. Like you said, camphor is neutral, but caffeine's not. Well, caffeine's a neutral molecule. I would prefer you look at it just in terms of charge. If you're talking about it not being acidic or basic, then just say that. Neutral means no charge to me, and I think to most organic people. Both of these are neutral compounds. They're both dissolved here. But we can add in maybe some aqueous sodium hydroxide. That's not going to mix with this, so now we got two layers. It's called water here, but it's basic water. It's hydroxide. Okay? It's aqueous base. And we can shake this up and partition it. And this compound, the question is, can hydroxide turn one of these into an ion? Well, we know that's a carboxylic acid, right? Yes, hydroxide is going to react with that and convert it to an anion. pKa is about 5. pK of water is 16, so that side is going to be favored. Okay? And when it's in the anion form, it's now going to favor the water layer. But this compound is not acidic. Its pK is 16, and hydroxide will not deprotonate it. It will never become an anion, and so it will always remain in the dichloromethane layer. So essentially, we now have partitioned the compounds or separated them. This one is in this layer, that one's in that layer. We can separate the two layers into two different flasks, and we've separated the compounds. This one can be recovered by maybe distilling off the dichloromethane and just leaving this in the flask, which would be non-volatile. After you've evaporated the solvent, then you have that separated. This one's in the anion form. You can boil off the water. That's a little difficult. If you want back to neutral, what do we have to add to this to put the H back on?
Acid.
Acids put H's on, right? What acid would you add here? Anybody have a suggestion? What would you add to this? It's in the flask. What would you add to it? What acid? What's your favorite acid? HCl. What's that going to do? These electrons are going to take the H, and you're going to get back your... By the way, the benzene ring is often denoted as a phenyl. You'll put the H back on, and if you want to balance it out, you'll form sodium chloride, right? When we go back neutral, if this is in water, if this is no longer soluble, it may precipitate. Precipitation? Because it's now neutral. If it does, then maybe you can just filter it off, and then you would have it separated. If it doesn't precipitate, well, then you have to do a little bit something else to get it out. But we've separated two components using acid-base chemistry because one of the components will be converted to an ion with the base, but the other will not. And if you understand pKa's, pK of this is about 4, this is about 16, much less acidic. And so understanding pKa's extraction solubility, opening statement is ions prefer water, neutral prefers organic, right? Number of exceptions. Okay, any last things here? Question?
Can you go over number 7 on the physical properties formula?
I send you the answers, right?
Yeah.
Okay. Ask during the review session because we're about out of time. We're out of time. We'll talk about test format on Friday, and we will likely have a quiz on Friday. Our last quiz before the test on Monday. Have a good day, guys.